We're going to go over the kinetics warm-up. In the first part, when you're given the rate of disappearance or of appearance of one component in a reaction, you actually can use the balanced equation, which is a no-no for finding the rate law, but we're not finding the rate law here. We are just saying that in terms of C, which does have a coefficient of 3, here is the rate. So you can see that the disappearance of A, this reactant, since it only has a 2 as a coefficient, is going to be slower than the disappearance of C, and it will be 2/3 the rate of letter C. So we're going to get an answer here of 0.200 molar per minute, and that would be the rate of disappearance of A. Now, since I already have the word disappearance here, you don't need the negative sign. A negative implies that it's disappearing and that you have a reactant that you're taking a look at. We have to determine the rate law. So we are going to look, in order to find the the exponent for A, we want to find a spot where the B concentration and the C concentration stay the same. They don't change. So it looks like trials 2 and 3, that works out well for us. If we look at trial 3 compared to 2, the concentration is going to increase by 3 times 3, but the rate stays essentially the same. Okay, so your rate ratio will be equal to 1, and then if we are multiplying by 3 the concentration of A, so 3 to what power gives us 1, that gives us the order of reaction with respect to A as 0. Okay, so we can cross this out and put a 0. Now, really, you wouldn't even have to write that because anything to the 0 power is 1. Okay, so now we're going to figure out the order of the reaction with respect to B. So let's find trials where A concentrations and C concentrations stay the same. It looks like if we compare 4 to 3, these guys are constant, these guys are constant. So from here to here versus the rate from here to here. So the rate is increasing by 3, and the concentration here is increasing by 1.75. Okay, so our rate ratio is 3, and then we have 1.75 to some power. If you take the log of both sides, and then remember, you can move this exponent out in front here, and you solve for n, you get like 1.96, which is approximately equal to 2. So we'll just say we can only have whole number orders. So then n, we now know, is 2. And then finally, to find the order of the reaction with respect to C, we'll do a comparison of 2 to 1. So the rate increases by a factor of 3, and actually the concentration of C also increases by a factor of 3, where the A and B concentrations stay the same. So the rate ratio is going to be 3, and that's going to be equal to 3 raised to some power. Very easily, you can see P is equal to 1, so the order with respect to C is 1. Okay, so in purple, I wrote the rate law. A to the 0 power is just 1, so I didn't even write it. Now we just have to pick one trial and sub in the values in order to calculate a value for K. So I'll just pick trial 1. So I just subbed in from trial 1, and then the value is 5.95. To figure out your units, we have molarity per minute is equal to K, and then over here we have a total of molarity cubed. So if we divide both sides by molarity cubed, we'll get molarity per minute divided by molarity cubed here. So one of these will cancel to make molarity squared. This will completely cancel. That'll be equal to our K. And then if we simplify that, it's going to be molarity to the negative second minutes to the -1. There are obviously other ways you could write that. And there we have our units. Okay, the purpose of this question is just for you to compare and contrast the differential rate law, which is what we used previously, and integrated rate laws. So what data would have to be collected in this experiment? It's going to be concentration and time data, whereas differential rate law, it's concentration, but rate. So time's a little bit easier to measure. And then remember what you do, you just plot your different relationships to figure out what order it is. Also, notice we're dealing with D decomposes into however many products. You're limited for integrated rate law to one reactant systems, otherwise it gets overly complicated. So if it is second order, that means we plotted 1 over concentration versus time. The versus time never changes, it's just this factor here. So 1 over concentration specifically of our reactant D. And remember, when you have second order and you'd be plotting this, you're going to get a positive slope. So if you had the slope of this line, and of course the integrated rate law for a second order reaction, which is 1 over, in this case, concentration of D is equal to KT plus 1 over the concentration of the initial concentration of D. Notice that your slope comes right from this. It's not negative. In 0 and first order, remember the slope, if you're taking it from the equation of a line, is going to be the opposite of your K value. But here, your slope and K are equal. Okay, just remember that a reaction profile has units of reaction progress on the x-axis and potential energy on the y. In this case, we have a delta H. A lot of times they're not quantitative, but this one is. We have a delta H of -30 kilojoules per mole. So that means it's an exothermic reaction. So your reactions are going to be higher in energy compared to your products. So let's say we start our reactants off at 40 kilojoules. That would mean our products would end at 10 kilojoules. But remember, it's not just a straight shot. So the shape of this has to have a little hump, right? And that hump is the amount of energy between the reactants and the peak is called activation energy. So this particular activation energy is plus 10. So that means that we are going to start at 40 kilojoules. Our hump will go to 50, and then it'll round out down here at 10 kilojoules. So just to label these from here to here, that's our delta H. And then from reactants to the peak, that's our activation energy. The next question says, what is the effect of drawing, of adding a catalyst? So a catalyst is just going to lower activation energy. It does not have to be quantitative. Just show like a dotted line that has a lower hump, but everything else stays the same. Obviously, the potential energy of your reactants in your products, and then we'll just say with a catalyst is that dotted line.